Hello everyone, my name is Reactors. I will be discussing how materials used in a boiling water reactor, or BWR, can degrade or fail over time, as you know, due to process variables, especially under unexpected pressure changing. We will explore two critical areas inside the primary circuit: the reactor pressure vessel wall and cladding, and the circulation piping with its different material weldments required time to time. And for each, I'll describe how the failure might occur and what measures can be taken to prevent it. As you know, there are several types of BWRs available worldwide, and let's specify some general boundaries. Boiling water reactors operate continuously under high pressure and high temperature conditions, roughly 102 psi or 75 atmospheres and 285 degrees Celsius. Over decades of operation, these conditions push materials to close their design limits, even strict design criteria or allowances. The goal of the analysis is to identify two areas within the primary pressure boundary where a sudden pressure increase could maybe cause the failure on the pressure vessel or piping system. I would like to focus on the reactor pressure vessel and its cladding, and then on the circulation, recirculation piping and weld joints connecting the internal systems. The first critical location is the reactor pressure vessel wall and its stainless steel cladding. The vessel shell is typically made from low alloy steel, while the interior surface is clad with type 308 or 309 stainless steel for corrosion protection. As you can see, general material in USA-based BWR material types in the table. After 30 years of neutron bombardment and thermal cycling, this region can experience embrittlement, a reduction in toughness that increases the risk of brittle fracture, especially during the rapid pressure changings. The inconsistent thermal expansion between the cladding and the base metal can also create residual stresses which promote the lamination or cracks. Over time, fast neutrons hit the steel in the reactor vessel and knock atoms out of place, creating tiny defects on the surfaces, and these defects make the steel more brittle, meaning it can crack instead of bending if there is sudden pressure surge or changing. To prevent this, power plants use special radiation-resistant steels and regularly check test samples and following NRC guidelines. They also run safety analysis called pressurized thermal shock tests to make sure the vessel can handle pressure spikes. If embrittlement is found, heating the steel can help restore some flexibility, and ultrasonic inspections are used to spot crack early before they grow. The second high-risk spot is the recirculation piping system, especially at the welds where stainless steel pipes are joined to nickel-based alloys. The metals used here, 304 stainless steel alloy steels, and react differently to the hot reactor water and the stresses from temperature changes. The most common problem is called intergranular stress corrosion cracking, IGSCC, where tiny cracks from along the grain boundaries of the stainless steel under stresses. These cracks grow slowly over time, but if there is a sudden pressure spike, they can quickly expand and cause leaks or even a pipe rupture. This is one of the worst case. The recirculation loop carries high temperature water that contains oxygen and radiolytic species like hydrogen peroxide, which can affect the metal's microstructure. The risk is highest where different metal meets. It causes galvanic corrosion can occur, and welding leaves tensile stresses that encourage cracks to grow. To reduce these risks, plants often replace old nickel-based welds with modern alloy like 690 or 52 or 152. This uses hydrogen water chemistry to limit oxidizing and apply surface stress techniques such as shot peening or weld overlay. Regular inspections following ASME rules help catch cracks early. In the US, the reactor vessels studs are the parts most likely to see fatigue damage if needed. This is another topic. These studs can be replaced, and fatigue becomes a bigger concern if cracks are detected during inspections or if the plant's operating life extending purpose. For most other components like nozzles, penetrations, safe ends, and the vessel skirt, actual operating history often shows they can safely last longer than initially predicted. To conclude, both the reactor pressure vessel and recirculation loop are key components in the BWR's pressure boundary. The vessel is vulnerable to radiation embezzlement, while the piping system is prone to stress corrosion cracking. By combining proper material selection, chemistry control, surface stress management, and ongoing inspection, these risks can be effectively mitigated. And following ASME, NRC, and the International Atomic Energy Agency standards ensures the continued integrity and safety of the reactor. Even as it operates beyond its original design life, it's possible. Thank you for watching the video, and I hope you enjoy and learn some new things. Thank you.